So what I have out here is an aqueous solution of vanadium in the +5 oxidation state, and if I stir this solution in the presence of zinc mercury amalgam, the color of the solution is actually going to keep changing. So what's going on out here? Well, the zinc mercury amalgam is a mixture of metals, and metals can lose electrons. Now if I agitate this mixture, I can force some of the electrons to go from the metal to vanadium +5, thereby reducing it to vanadium +4, which is blue in color. And if I agitate it some more, I can force even more electrons, thereby reducing it to vanadium +3, which is green. Now another cool thing about this reaction is that if I keep it out in the open, the vanadium +3 can actually react with oxygen out in the air and can get oxidized back to vanadium +4 and +5. Now vanadium is not the only element that shows such a variety of readily accessible oxidation states which differ only by 1 unit. In fact, all of the transition metals show such variety in oxidation states. Now this is actually very different compared to, let's say, the S block elements. So the alkali metals only have an oxidation state of +1, while the alkaline earth metals only ever show an oxidation state of +2. Similarly, if you look at the P block metals like aluminium, gallium, indium and thallium, they have an oxidation state of either +1 or +3, while germanium, tin and lead can show an oxidation state of either +2 or +4. So the next question that automatically arises is that why do these transition metals show such a wide range of oxidation states? Well, the answer to that question is that in the D block elements, we have these inner D electrons that can actually take part in bonding. Also, these inner D orbitals and the outer S orbitals are actually very closely spaced to each other in energy. So if you look at the 4s and the 3d orbitals, you can see that they are very close to each other in energy. So therefore, if you look at the successive ionization energy data of a transition metal like manganese and compare it with, let's say, an S block metal like magnesium, you can see that while it takes almost similar kinds of energy to knock off the first 2 electrons, the third ionization energy in case of magnesium is much higher compared to that of manganese. Well, this is because to take out the third electron, we actually need to take it out from a very stable noble gas electronic configuration in case of magnesium, while in case of manganese, we simply have to take it out from an inner d orbital. Now because these 3d and 4s energy levels are very close to each other, it only takes a slightly higher energy. And therefore, because it is relatively easier to knock off these d electrons, the transition metals show a wide range of oxidation states. Now in the D block, you can see that the variety in oxidation state, that is the total different oxidation states that a transition metal can have, keeps on increasing as I go from left to right. It reaches a maximum at manganese. So manganese can have an oxidation state ranging from +2 to +7, and then this variety keeps on decreasing, right? In fact, zinc can only show an oxidation state of +2. Now this happens because while the +2 oxidation states, the lower oxidation states are ionic, the higher oxidation states like +7 of manganese is actually covalent. So while manganese 2 chloride is mostly ionic, made up of manganese 2 plus and chloride ions, compounds of manganese in which manganese is at a high oxidation state like the permanganate ion, these compounds are covalent. This is because only highly electronegative elements like fluorine or oxygen can pull so many electrons away from manganese, and even then these electrons are not completely transferred because manganese has such a high positive charge, so it can pull electrons back, and ultimately there is sharing of electrons. So there is a covalent bond between oxygen and manganese in MnO4-, and similarly other compounds of transition metals in higher oxidation states like the dichromate ion are all covalent. Now as we move from the left to the right, the total number of d electrons keeps increasing, right? Remember, both the d and s electrons can take part in bonding, and to make covalent bonds we actually need half-filled orbitals according to valence bond theory, and it's actually relatively easy to unpair the s electrons. So manganese, because it has a maximum of 7 valence electrons, it can form 7 covalent bonds with highly electronegative elements like oxygen, and thus it can have a maximum oxidation state of +7. However, as we move to iron, cobalt, nickel, copper and zinc, the d orbital starts getting filled up. There are too many d electrons, hence there will be fewer orbitals available in which to share electrons with others. Also, as we move from left to right, the total number of protons increases, so it also becomes much more difficult to ionize or unpair the inner d electrons. In fact, in zinc, the inner d electrons do not at all take part in bonding, and zinc thus can only have an oxidation state of +2. So the possible oxidation states of the 3D series is actually very easy to remember. It's in the shape of an inverted pyramid. Now the most common oxidation states of these elements are actually highlighted in yellow. Now towards the beginning of the series, the higher oxidation states are more common, and this is easy to explain. Removal of all the valence electrons leads to the formation of a very stable noble gas electronic configuration. So that's why these oxidation states are fairly common. Manganese can also show a +2 oxidation state, as the D5 electronic configuration is also relatively stable, while chromium also commonly exhibits a +3 oxidation state. The D3 electronic configuration is also stable in case of chromium, but we can't explain it right now. We need crystal field theory, which we'll talk about in a later video. On the other hand, as I move from iron to zinc, we have seen that the higher oxidation states are not possible, so the lower oxidation states are more common. Now as we go down the group in the D block, the stability of the higher oxidation state actually increases. So if you look at chromium, molybdenum and tungsten, the stability of tungsten +6 is actually much more compared to that of chromium +6. Similarly, if you look at iron, ruthenium and osmium, while iron generally shows +2 and +3 oxidation state, osmium can in fact exhibit +8 oxidation state in osmium tetraoxide. Now this happens because as we go down the group, the d orbitals becomes much bigger in size, they are much more diffuse, they can overlap much better with a surrounding atom, and coupled with the fact that they have an increased nuclear charge, they can actually form really strong covalent bonds with electronegative elements like oxygen. Now this is really different from what we have seen in the p block. For example, if you look at aluminum, gallium, indium and thallium, the stability of thallium +3 is actually less than that of +1, and similarly the stability of lead +4 is less than that of lead +2. In the p block, this happens because the increased nuclear charge causes relativistic effects on the ns orbital. 6s orbitals shrinks and faces a much greater pull from the nucleus, and therefore it becomes really difficult to unpair the 6s electrons, which becomes inert towards bonding. So this is what we call the inert pair effect, right? So in thallium, it's very difficult to make thallium +3. We can only take out one electron from the 6p orbital, so thallium plus is more common. Similarly for lead, lead +2 is more common compared to lead +4. Now because the d metals can access a wide variety of oxidation states, they play an important role in making many interesting stuff like rechargeable batteries. They are also very important industrial catalysts, and they play subtle but very important roles inside biological systems.